The 11.3 quick check is talking about the ideal gas law. So what we're first do is say PV equals nRT. Here's the gas law. What units do we have to use? For pressure, it has to be in atmospheres. For volume, it has to be in liters. And it's going to be in moles no matter what. That's not a big deal. R is liter atmospheres per mole Kelvin. And temperature has to be in Kelvin. The value for this 0.0821 liter atmospheres per mole Kelvin. So ideal gas law problems for each one of these, and we're looking for these various variables. So here we see 3.50 liters. That's a volume. And a pressure of 2.80 atmospheres. Okay, 40 degrees, which we're going to immediately change to 313 Kelvin. And we are looking for the number of moles, and we know that this is 0.0821 liters atmospheres per mole Kelvin. Okay, so we're solving for N. So we have PV equals nRT. So I would say that this is N equals PV over RT, and all of our units are in the right units already, so we're just going to go and substitute those in. And so we're going to have 2.80 atmospheres times 3.50 liters divided by 0.0821 liter atmospheres per mole Kelvin and 313 Kelvin. When I do this, I get an answer of 0.381, and this is moles, because we're defining this as moles. And hopefully that's the right answer. Certainly the setup is correct. Okay, the second one here, a 1.25 mole sample of nitrogen, and it's a 5-liter container. If the temperature is 25 degrees, which we're immediately going to change to 298 Kelvin, what is the pressure? And we know that this is 0.0821 liter atmospheres per mole Kelvin. Now again, all of my units are correct except for Celsius, and I fixed that. So I'm going to solve for this here. So PV equals nRT, which means P equals nRT divided by V, and I'm going to substitute in, and so I have 1.25 moles, 0.0821 liter atmospheres per mole Kelvin, 298 Kelvin, all divided by the volume, which is 5 liters. And this answer is going to come out to be in atmospheres. And the value I get, 6.116, so I'm going to say 6.12 atmospheres. Okay, next problem. A syringe containing 50 milliliters, okay, 50 milliliters, so that's my volume. But I can't leave it in milliliters. I know that there's 1,000 milliliters per liter, which is the same as moving my decimal point, so 0.050 liters. Has a pressure of 225 kilopascals, but I can't leave it in kilopascals, so I know there's 101.3 kilopascals in every atmosphere, so that comes out to be 2.221, that's close enough, atmospheres. Okay, contains how many moles? So this is what we're looking for. R, we know this is 0.0821 liter atmospheres per mole Kelvin. And the temperature is 20 degrees, which we immediately changed to 293 Kelvin. So again, I'm looking for moles. So like we did before, we'll say so PV equals nRT. N is equal to PV over RT. And now I'm going to substitute in. And when I do that, I get a pressure 2.22 atmospheres times 0.050 liters divided by RT, 0.0821 liter atmospheres per mole Kelvin, and 293 Kelvin. And I'm getting a pretty small number, 0.004616, so I'm going to say 462, and this is moles. Okay, so again, this is pretty much straightforward kind of problem, except that we had several things to change. That was in kilopascals, so we had to change it to atmospheres. The volume was in milliliters, so we had to change it to liters. And as always, Celsius has to be changed to Kelvin. So with those conversions, we just plug and chug, and 0.00462 moles. Okay, the last one. We have a 5-liter metal container. Okay, that is 32 grams per moles oxygen. Okay, has a pressure of 3 atmospheres at 100 degrees. What is the mass of oxygen? So what do we know? We know that this is 3 atmospheres, and that's the correct unit. And we have 100 degrees Celsius, which is 373 Kelvin. So that part's okay. We know that R is 0.0821 liters atmospheres per mole Kelvin. And what do we have? A 5-liter container, 5.0 liters. So the only thing that we don't know is number of moles. So we're going to get moles. Okay, so since N is the only one we don't know, when we're looking for mass, I know if we find the number of moles, we can convert it to the mass because we know the grams per mole. So we'll do that as a separate step. So first off is solve for N. So we know PV equals nRT. So therefore N is equal to PV over RT. And we're going to substitute in our values. So 3 atmospheres, 5 liters, 0.0821 liter atmospheres per mole Kelvin, and 373 Kelvin. So for this I get 0.48982311, and that is moles, and this is moles of oxygen from the problem. And that is not our final answer, but that's what we're going to use next. And using the fact that we know that the molar mass of oxygen is 32, I'm going to say if I know I have 0.4898 moles of oxygen, and I know that every 1 mole of oxygen is 32 grams of oxygen, then I just take this answer and multiply by 32, and I get 15.67, I'm going to say 15.7 grams of oxygen, and that is my final answer for this problem. So what is the mass of oxygen in the container? We calculated. So we had to do PV equals nRT, and then do one final step using the molar mass, and that is the quick check.